Hello everyone. We continue our discussion of perspective projections. So we have seen that perspective projections make parallel lines appear to converge in the resulting image, and the point at which these lines appear to converge are called vanishing points. Yes. Now I want to talk about this idea of non-uniform foreshortening before we move on. So if you have a railway track, for example, right? So a railway track might look something like this, right? So the structure of the railway track is such that the distance between these horizontal bars is the same, right? So let us say that this distance is d, right? And you take an image of the railway track from a camera placed at this location. Okay. If you do that, then you will potentially see an image that looks like this, right? So in the image, you are likely to see that the railway tracks converge like that, and the first horizontal bar will appear here. The middle horizontal bar might appear there, and the third horizontal bar might appear there, right? So what we find that so this is the world, and this is in the image. Okay, so the vanishing point is going to be somewhere there, right? This is the, and if I measure the same distance d on the image, yeah, then the same distance d, sorry, this the same distance d is going to appear as some distance d prime between these two, and a different distance d double prime between those two, right? So d does not always appear as the same length on the image. It covers more pixel if you are closer to the camera, and it covers less pixels if you are further away from the camera. So you can see the same phenomena being repeated here in an actual image. So this distance seems to cover some number of pixels here, whereas it covers far fewer pixels when the same distance is farther away from the camera. Okay, so this is what I mean by foreshortening. So the foreshortening is new length by original length. So this is the foreshortening at this location, and the foreshortening at the other location is d double prime by d, right? So this foreshortening is not uniform, and the reason that this happens is because in the perspective projection, if you remember, there the matrix has if it is a perspective projection, then the matrix has a form like this, right? It has zeros everywhere, and it has this R here. Okay, so when you dehomogenize the point, it is going to produce x prime that is x divided by 1 plus rz, and y prime that is y divided by 1 plus rz. Okay, so this division by the z coordinate is what is causing the non-uniform foreshortening. Okay, so it really depends upon the distance from the camera, and that is what causes the foreshortening. And because the distance from the camera varies as you move further away into the world, the foreshortening also changes. Okay. Now we try to characterize perspective projections using the vanishing points, or rather the axial vanishing points that appear in the image. Axial vanishing point. Okay. So before we can actually write down the math for vanishing points, I want to make a small observation about homogeneous coordinates. So remember, we had said that a point xyz in 3D Euclidean space maps to a 4D homogeneous point xyz1, right? What if we are given a vector in Euclidean space? So if V, instead of being a point, is a vector, right? It represents a direction. So direction what if V represents a direction like this? Okay. In such a case, the homogeneous representation for V is going to be x, y, z, 0. So what this means is that it represents a homogeneous point at infinity. So it is a homogeneous point at infinity in the direction of V. Okay. So if you remember the geometry of the homogeneous representation, when we went from 2D Euclidean to 3D homogeneous, we said that we had a plane which was the W is equal to 1 plane, and any point in 2D Euclidean became this, if this was the point xy in 2D Euclidean, it became the point xy1 in 3D homogeneous, and then it really became this ray, right? Because all these homogeneous points on the ray map to the same Euclidean point. By setting the homogeneous coordinate to 0, we can treat points at infinity or analogs to directions in 3D Euclidean space as normal points in homogeneous space. So we see that homogeneous coordinates now lend themselves naturally to these descriptions of points at infinity. Okay, they give us a very nice machinery to handle these points, and we will use this to get a sense of where the vanishing points lie in our image. Okay, so to find the vanishing point along the z direction, we say that the vanishing point in the z direction is the point where lines parallel to the z axis appear to converge, right? So the direction of lines which are parallel to the z axis is the same as the direction of the z axis. That direction can be represented in homogeneous coordinates as follows, as 0, 0, 1, 0. Okay, so this is the homogeneous representation of the point at infinity in the z direction. Yes, we multiply this with our perspective transform, and what we get is 0, 0, 1, r. Okay. Now, if you dehomogenize this point, you will get x prime equal to 0, y prime equal to 0, z prime equal to 1 by r. So this gives you the coordinates of the vanishing point, right? So now if you set r equal to minus 1 by zc, then you see that z prime is equal to minus zc. Yes, because if you set r equal to 1 by zc, then z prime is going to be equal to minus zc. That means that the vanishing point lies an equal distance on the opposite side of the projection plane, right? So if this is a z-axis, right, and zc is your camera center, then the vanishing point lies at minus zc. Okay, So all lines which are parallel to the z-axis will in the image will appear to go and converge there. Yes. So when an image has one axial vanishing point, it shows one axial vanishing point. It is called a single point perspective image. Okay. And the perspective transformation is called a single point perspective transformation. Right? So just like you can put your camera center on the z-axis and get the z-axis axial vanishing point, you can similarly have your center of projection or the camera center on the x-axis, and that gives you the corresponding perspective transform matrix. So instead of R here, you have this P here. The coordinates look like this, and the center of projection is at that location, and the vanishing point is equal distance on the opposite side of the projection plane, but on the x-axis. Similarly, you can have a single point perspective by putting the center of projection on the y-axis and having this Q here instead of P or R. Right? So depending upon which axis your center of projection is on, you can have different single point perspectives. Okay? And they result in their corresponding axial vanishing points. Okay. Now, can you have more than one axial vanishing point in the image? Yes, you can. So look at this image. For example, this is a sketch, but it does not matter. Same thing can happen in an image. Here the vanishing points are in those directions. Okay, and there is no vanishing point in this direction, in the vertical direction. These are parallel. So how do you get this sort of an image? This sort of an image which has two axial vanishing points is called a two-point perspective, right? And the way you get this transform is by multiplying two single point perspective transforms. That gives you a two-point perspective transform. So you just have P and Q here, and you can see that the image point will have the following coordinate, where in the denominator you will now get Px plus Qy plus 1 when you dehomogenize. Okay, so you will get two axial vanishing points. That is the characteristic of the two-point perspective transform. However, will you also get two centers of projection? Right? Is that physically possible? That the camera is in two places at the same time while taking the same image? That sounds a bit implausible, right? So where is the center of projection in this case? Right? So think about it for a while. We'll come back to this question in a minute. You can also have a three-point perspective because there are three axes. You can at most see three axial vanishing points. So if you multiply the three single point perspectives, you will get all three of P, Q, and R here instead of zeros, and you will get three axial vanishing points. So this is a very good example of a three-point perspective image. So you have the vanishing point in the y direction, you have the vanishing point in x direction, and you have the vanishing point in the z direction. Okay, or that is z and this is x, does not matter. So this is a painting by M.C. Escher, and if you haven't looked at Escher before, I suggest you go and Google him and look at his painting. So this particular one is called Ascending and Descending. So if you look closely at this staircase, you will find that these people who are drawn here are always going up or always moving down. So this is like an impossible staircase in this diagram or in this drawing, but the drawing has three-point perspective. Okay, so three-point perspective drawings or three-point perspective images or images formed under three-point perspective transforms have three axial vanishing points. But again, the question arises, do they have three centers of projection? And that does not seem likely, right? Because you cannot put the camera center at three locations at the same time to create just one image. So what is happening here? How are we creating the 2-point perspectives and 3-point perspectives? Well, let us look at this case. What happens if I transform my object and then apply a single point perspective? Okay, so this is a single point perspective projection because I have zeroed out the z coordinate. But before that, I have applied a translation. So LMN is a translation. Okay, so this is the matrix, but this does not give me geometric intuition. So if I look at it visually, then visually we can see that if I do a translation in X and Y, then when I was centered at the origin, say this was my shape, then I could see only one side of the object. However, when I translate along the XY line, more faces of the object come into view. Okay, so I can see more of the side face and the bottom face there, and I can see more of the top face and the other side face here. Okay, so this is translation in the XY direction. Translation in the Z direction, which is the principal axis in this case, causes zoom. Okay, so if let us see, if this was my object, right, to start with, then the size of the object in the image was given by this. Okay, the size of the object in the image to start with, this is D. If I translate this object further back or I move it away from the camera, then the size of the object in the image becomes smaller, right? It goes down to D prime. However, if I move the object closer to the camera center, then the size of the object in the image becomes larger and I get D double prime. Okay, so translation along the Z axis is causing scaling, or as we also know this phenomena, zoom. Okay, so camera zoom is obtained by changing the distance between the object or the world and the camera. Okay, so this was applying a translation and then doing a single point perspective projection, right? We can also rotate, so we can rotate about the y-axis and then do a single point perspective transform or projection. If we do that, the resulting matrix is very interesting. You see, in the resulting matrix now, I have a 2-point perspective. So now our question about the two centers of projection becomes clear, right? So how do you obtain a 2-point perspective image like this? You hold your camera and you move in your world so that your world rotates with respect to the camera, right? So if you had taken your image from, say, here, you would have gotten a single point perspective, but you moved to this point, right? And you took an image from here, so you got a 2-point perspective instead. Okay, and this is proved by this simple multiplication of matrices. You rotate your world, so the world point is going to appear here as a vector. So you rotate your world about the y-axis and then you take a single point perspective and you get a 2-point perspective. If you do 2 rotations, one about the x-axis and one about the y-axis, and then apply a single point perspective projection, you get a 3-point perspective. Okay, so that is how you generate a 3-point perspective image. You rotate twice. So you once move the camera along the x-axis, along the y-axis first maybe, and then along the x-axis. Actually, it does not matter. You can try the other order. That should also give you a 3-point perspective. Okay, so this sort of finishes our discussion about viewing transforms, right? So we have looked at various kinds of projections, and these are all planar projections. Why are they planar projections? Because our surface of projection is always a plane. We are projecting only on planes, right? There are other kinds of projections. You can project on paraboloids or hyperboloids. So you get paraboloid projection or hyperboloid projection and so on. We are only interested in planar projections. And we have seen two broad categories of planar projections, parallel and perspective. In parallel, we saw orthographic, axonometric and oblique. And in perspective, we saw 1 point, 2 point and 3 point perspective. Okay. We will continue our discussion of viewing transform by moving further in the modeling viewing pipeline and figuring out how do we apply our viewing transforms in practice to simulate the image formation process in our pipeline. Okay, that is what we will see in the next lecture. Thank you.